First off, you might see I'm wearing a fanny pack. I'm not trying to set a new fashion statement, nor do I have any association with ISIS. So you don't have to worry about me pulling the plug and this place blowing up. I'm undergoing some chemo treatments, so this is kind of a nice lead-in to my topic today because it does use a sampling pump. Not that it was planned this way by any means, nor did I really want to have it planned that way. This is our game plan for today. I've got a number of learning objectives, and like I said, this is a really big topic to try to make something out of. So we're going to try to provide that 10,000 foot view, and every so once in a while come down to the 5,000 foot level and then bounce back up. To cover this particular topic would probably take at least a couple of good 8-hour sessions just to get all the points. But we'll give you enough information just to make you dangerous. First item up is why monitor? Okay, that's one of the first questions that usually comes up. A very good one is for compliance reasons. Certainly within the OSHA standards, there's nothing specific with regard to requiring any kind of monitoring of individuals other than specific standards such as lead, cadmium, hexavalent chromium, asbestos. But when it comes to grain, there really isn't anything. That doesn't mean that OSHA could not cite you because they could use the general duty clause for that particular purpose. And they have. I've seen and read some situations in the past where a facility has been cited for not monitoring individuals based on the general duty clause, which is kind of a catch-all. The other part of that is just recently, within the last week, I noticed a client that we still provide some services here in town, but he sold the company. His company was hit with a $1.4 million fine for not monitoring their individuals for exposure to lead during the refurbishing of a ship. He owns a shipyard as well. 10 willful violations. And with the increase in OSHA fines, they're now going to be moving up 70% from where they were at. Good reason maybe to think about doing some monitoring. Another reason why is litigation. You have an employee that may come down with some sort of an illness that he or she may point back to the company and say, hey, I had this exposure based on the fact that I handle these particular materials. If you don't have any sampling data to back that up, guess what? In all likelihood, you're going to lose. The other side of that is employees can call OSHA, and they can voice a concern, which means that you might get a notice, and then you would have to respond to that via sampling within a 30-day period. Another reason for monitoring is a proactive approach. You want to try to get out ahead of everything, and you might, in some cases, want to be on the OSHA VPP program. Another reason for conducting monitoring, you want to make sure that the health of your employees is such that the operations and tasks that they're conducting aren't subjecting them to any kind of exposure. And then finally, another reason for monitoring is to find out how adequate the controls are, specifically with respect to engineering controls that may involve local exhaust ventilation. So there are numerous reasons for wanting to monitor. And there are 3 different types of monitoring. Typically, when we talk about monitoring, one of the first ones is environmental. We're not going to dwell on that today because that's kind of a separate topic all itself. But typically in environmental monitoring, it's a perimeter type of monitoring because you're trying to determine just exactly whether or not the operations and the materials that are generated at that particular facility are migrating off the site and impacting your neighbors. Second, monitoring is area monitoring. And typically this is conducted to try to find out what the contaminant is and where it's being generated. This also comes in handy, like I said before, with respect to determine whether or not your local exhaust system is doing its trick. And finally, the one for compliance purposes is personal monitoring. And this is where you're actually equipping the individual with a pump and a certain sort of media in order to collect that sample, sending that in and having it analyzed. To kind of give you an idea, the view at the right here shows area monitoring. You got a stand, here's the pump down here, and you got your media up here. And you're collecting information on this, and you notice that there's nobody in here. Typically we use this for indoor air quality studies, trying to find out what the culprit might be that's causing individuals' sickness within the building. On the right here is a setup for monitoring, personal monitoring. You have a pump here, Tygon tubing, and collection media. One of the things you also have to take into consideration with respect to sampling is the sample duration. If you look off here to the left, grab sampling, typically grab sampling is something where you're trying to get an idea what you might be dealing with. You just want a quick and dirty way of trying to get an idea of what the material is, or you can also use that for the purposes of determining whether or not you have a noise hazard. Typically that particular sampling takes about 1 to 5 minutes. You usually get a fairly direct readout from that particular sampling. It's not going to be great for any kind of compliance purposes. What you're trying to do is just get an idea of what you might be dealing with so that you can set up and then conduct some of the other types of sampling. You also have partial, which now we're getting to some of the OSHA requirements with respect to exposure limits. And the partial usually is to determine either a short-term exposure limit or a STEL or a ceiling concentration. Usually these are, as you say, short-term samples. So you're collecting the sample over a 15 to 30-minute time frame. And then finally, you have what's referred to as a full shift sample. And this is in order to determine what the time-weighted average is for that exposure. Usually that is collected over an 8-hour time frame. Now all of the OSHA limits are basically set up on an 8-hour time frame. It goes back a number of years. Keep in mind that people work 10-hour, 12-hour shifts. The only standard that I know of that OSHA has in place that allows you to lower the exposure limit is lead. They actually have a formula that you use. But for all of the other exposures, typically that exposure is based on an 8-hour time frame. There's also a sampling strategy to consider. Are we going to use a random type of approach? Usually with the random approach, you try to get an overall view of what's going on in the facility itself. You'll see some seasonal differences. Certainly in the summertime, doors are open, humidity usually keeps a lot of things down, whereas in the winter it's a little drier, at least around here. And with that, the winter usually are closing doors up. So it's a little tighter situation, a lot more potential for differences in exposure. Different tasks that may be conducted throughout the day that may involve the same material. You may, if you only do partial, you may only capture a portion of that particular task. And then, as I mentioned, sometimes the random sampling approach is used to determine how effective your controls are. Over time, local exhaust systems will end up losing some of their efficiency, and with that, you may end up losing some of that capability of pulling that material away from the individual's breathing zone. And for the purposes of personal sampling, the breathing zone is considered to be a 2-foot radius around the head. A lot of times, for sampling strategies, you look at a worst case scenario. Typically, this is primarily due to budget. You only got X amount of dollars to work with, so you want to try to get what you consider are the biggest concentration areas where you might have the potential for an exposure issue. So you'll look at where are those specific operations or tasks that I'm going to get a lot of material generated, as well as high concentrations. It's not going to give you the same kind of a picture as a random approach was, but in some cases, due to budgets, and all companies have budgets, it gives you some information with respect to those worst case situations. When we talk about air monitoring, there are some items that I'd like to go in a little bit further. One is the hazard assessment, the entry into the body, the various forms, and the exposure criteria. This will dictate just exactly what and how you're going to go about the sampling approach. Let's talk about the hazard assessment. Typically in a hazard assessment, what you're doing is you're looking at those operations and tasks that are going to generate an airborne concentration. Okay, so you go out, you'll assess, determine just exactly what you've got, and from that, get an idea of what those potential airborne contaminants are. Then if you've got access to safety data sheets, you would look at those safety data sheets, and from that, be able to pull out the components in the highest percentage in there, and if they have a specific exposure limit, you can target those particular materials, because typically those are the ones that are going to come off first with respect to an exposure. And then from that, what is very helpful is you can develop a sampling plan. Say you can't do all of it this year, but you can target some of the key areas and then next year hit some of the other ones. But the sampling plan allows you the flexibility then of being able to take a look and prioritize what you want to try to accomplish in a nice time frame. Then we've got to consider how contaminants get into the body. And typically there are 4 ways: inhalation, absorption through the skin, ingestion, and usually this is accidental ingestion. Usually you find heavy metals such as lead, cadmium, mercury, those type of items where if you don't wash your hands before you eat or smoke, you can actually take in lead and those particular materials via that route. And the final one is injection. Injection it came about typically because of AIDS, the HIV virus, hepatitis viruses that are transferred via contact with the blood. Primarily, when you're talking about facilities, you're looking at inhalation as being the primary way that materials get in the body, with absorption being the second method. And then we need to take a look at the contaminant forms. Are we dealing with a gas? A gas typically is a gas at room temperature. It fills the space equally. Okay? Or are we dealing with vapors? Vapors typically are a gaseous state of a liquid at room temperature that are given off. And finally, the one that probably is the most pertinent to what you guys are involved with as far as your industry are particulates. And particulates can have either be dust, they can be mists or liquid particulates, they can be fibers, or they can be fumes. And fumes are generated by heating a metal to a very high temperature. And you'll see the fumes in this picture being driven off. So those are the various forms that can be generated that you have to take a look at. Let's take a look with respect to some of the airborne hazards within the industry itself. You have those that are organic. Typically what we're talking about here was grain. Now, grain may also have some constituents associated with it. It comes in during the different phases of the farming process, bringing it in and then having it processed. You can also run into mold and fungi, and there could be some agrochemical residue still left through pesticides, insecticides, herbicides, fungicides, nematicides, and there may also be some fertilizers. Typically, with those type of things, they're just all put into grain dust per se. But those things can also be constituents that can cause, for some individuals, a reaction. Typically, when we do indoor air quality, individuals that are very susceptible to molds and fungi can react quite severely when those outbreaks occur. So you may have individuals that have that, but that usually makes up this constituent here of the grain. And then you may have some inorganic portions, because when it's harvested, you kick up dust, and that dust may have some silica in it as well as silicates. There also may be maintenance activities that you conduct at the facility, whether that be welding, which would generate fumes, or if you've got solvents that are used that would generate volatile organic compounds. So those type of things sometimes get lost because we're focusing on this grain aspect. Just to give you kind of an idea, grain dust itself is a pretty complex mixture. As you see here, it contains husk particles, cellulose hairs and spikes, starch granules, fungal spores, insect debris, pollens, and as we mentioned before, mineral particles. So that's the grain dust that you're looking at. You're not being able to separate any of that out per se. You're usually sampling for those particular materials. Now we've got an idea of some of the contaminants, the airborne contaminants. We'll look at the different types of approaches for monitoring of those particular contaminants. There are active and passive ways or methods to collect these particular contaminants. In the active method, you actually pull air through the collection media. If it's particulates, they would be collected on either a polyvinyl chloride or a mixed cellulose ester filter. If they're gases and vapors, typically they would be adsorbed as that air moves through the media. They would be adsorbed onto activated charcoal or silicate gel tubes or Tenex. There are a host of collection media for gases and vapors dependent on the specific type of material. In the passive approach, the collection on the media takes place via air currents. So you basically wear a badge, and the air current with the contaminant gets deposited on the media, either through adsorption. Again, they would use a activated charcoal media, or it would be a chemical reaction. So you'd have an inert type of material, you put a chemical on, the manufacturer puts a chemical on there, and it would react with that contaminant to form a color change. In the active method, here's the equipment that you use. You got a portable sample pump here, you got Tygon tubing, and then you got your collection media, which in this case is a polyvinyl chloride filter. This is referred to as the sampling train. There's also another piece of equipment that's used with these, and that's the calibrator. The intent of the calibrator is to make sure that you're using the correct flow rate to collect that particular material. And where do you find that information? Typically, there are sampling procedures that have been developed by NIOSH, which is the National Institute for Occupational Safety and Health, and OSHA, the Occupational Safety and Health Administration. What these sample procedures provide is a consistent approach plus a repetitive sample result each and every time you use the method. So it's been tested by labs, and these particular procedures provide the best approach with respect to sampling whatever material you're going after. And then in this approach, the samples are typically collected, then they're sent to a laboratory for analysis. In the active method, there's also equipment that can be used that provides direct reading capabilities. Here is a particle sampler. It also uses a pump, an internal pump, and it will pull in the particulates and you'll get a readout. Nice thing about this is that it does provide real-time results. However, you're going to have to follow whatever the manufacturer's operating manual says for making sure you're collecting the sample the way it should be collected. Here are some active sampling pumps. What you have here is, here's your pump, and you have the Tygon tubing, which goes up again to the sample, the collection media. In this particular case, this would be sampling for a total dust. When you put this little piece of equipment here, that's called a cyclone. And what the cyclone does is it goes after the respirable fraction of that dust. So anything that is 10 microns and less would be collected on the filter. The rest of it would fall out in the bottom of this little cyclone. So that's similar to a cyclone you would see for a local exhaust system, a control measure on the local exhaust, only on a smaller scale. In the passive method, you've got badges, and typically in the badge, you would slip this down. That exposes the activated charcoal or the media to the air, and passively, through air currents, would be deposited on that particular badge. You then also have colorimetric tubes, and here, this one is for formaldehyde, so you'll see a color change. This is kind of a yellow color here. There's kind of a pinkish color here. Either these can be passive, or you use a small little pump to pull the air through, and it provides a color change if your contaminant is in the air. These work out great for grab sampling, screening purposes. And then the last one is you can sometimes get individual gas monitors. I'm sure that some of you are probably familiar with those. If you've got confined spaces and you want to set the individual up, make sure that they're entering a safe space. Well, they do have individual monitors for specific gases. Not all of them, but they do provide a quick way of getting an idea of what that concentration is. And typically, again, like the passive dosimeters that we talked about, you typically have to go to the manufacturer's manual in order to determine just exactly how to operate and how much to sample and how they should be oriented on the individual. Analysis, with the badges, they're sent in to a lab. The other items provide, a way of reading the sample on site and getting your results quickly. Once you get those results back from the laboratory, now you have to interpret what it all means. And typically they will provide you with a result in a concentration unit. And those concentration units typically for particles are milligrams per cubic meter. If they're fibers, they would be fibers per cubic centimeter. And if you're looking at gases and vapors, typically you would be provided with a part per million part of air concentration, which otherwise refers to part per million, or ppm. Once you have that information, then you would look at what the exposure limit is for that, so you can do a comparison to find out if you're above or below the exposure limit. When we talk about exposure limits, there are three different types. You have, for compliance purposes, you have OSHA standards. These were actually taken from the ACGIH, which is the American Conference of Governmental Industrial Hygienists. So when OSHA came into being with its standards back in the 70s, they adopted the 1968 TLV booklet. And so back in about 1995, they tried to update all the standards, and you find these standards in the OSHA, they're referred to as the Z tables. There's a Z1, 2, and 3 table, and these are the established standards. Back in 1995, they tried to update, because some of them are pretty dated when you go back to the 68 time frame. That lasted all of about 3 months before the circuit courts threw it out. Reason being is there was a union that tried to say that one of the exposures wasn't low enough, and when the circuit court looked at it, they said, well, OSHA, you just can't randomly decide that you're going to update all these. You have to show justification, which means you would have to provide all the documentation to go behind that particular lowering of the exposure limit, which means with about 200 and some odd chemicals that have exposure limits, all of us would be well dead and gone before they'd even get through probably 10 of them, because the process is just a slow, arduous process that takes a lot of time. And you get input from companies and whatnot, and that's why unless they do something different, it's going to be very difficult. As I mentioned, these are the established standards, which you have to conform to. They refer to theirs as permissible exposure limits, or PELs. As I mentioned, ACGIH, which is the American Conference of Governmental Industrial Hygienists, they've been in this business since about the mid to late 50s with coming up with exposure limits. And theirs are updated on an annual basis. They take about 15 to 20 different substances, look at whether or not they should adjust those exposure limits down based on new animal data or new research. These, unfortunately, are recommendations. They're not mandatory. However, if you are proactive in your program and you use ACGIH limits, you're going to be well below the PELs. And you'll be out ahead in the event that they change a PEL. Theirs are referred to as threshold limit values. And one of the interesting things here is because this is a registered trademark, when OSHA adopted these, they had to come up with a different name. That's how you came up with PEL. You also have NIOSH, which is the National Institute for Occupational Safety and Health. They are kind of the research branch of OSHA. These guidelines, they're guidelines like the ACGIH, very seldom used. And they had to identify theirs as something else. So theirs are referred to as the recommended exposure limit, or RELs. So you have PELs, TLVs, and RELs. And just to give you kind of a flavor for the differences in these, if we're looking at grain, and typically OSHA does have a different standard for certain grains. So if you're dealing with wheat, oats, or barley, OSHA has an exposure, and this is actually total dust, if you want to call it total grain dust, of 10 milligrams per cubic meter. You'll notice that the ACGIH and NIOSH have lower exposure limits. Again, this is the mandatory, these are the recommended. For other grain dusts, they kind of fall into that nebulous category called particulates not otherwise regulated with respect to OSHA. For total dust, you're looking at 15 milligrams per cubic meter. If it's ACGIH, there's a lower standard there, 10 milligrams per cubic meter. And these they refer to as inhalable particles. They're insoluble or poorly soluble. And they refer to these, instead of PNOR, they call them PNOS, particles not otherwise specified. And you'll see as you go down, then you have other grain dusts. OSHA has established, at least for respirable dust, 5 milligrams per cubic meter, and the ACGIH 3. So that's what you would compare the results to determine whether or not, again, you're above the exposure limit or below, so that you can take the necessary actions in order to reduce that exposure potential to individuals. Okay, so that gets us through the air monitoring. We'll elaborate a little bit on noise monitoring. We need to cover some definitions here. We talk about sound. It's a source that sets air in a wave motion. Okay? Now, in talking about that, we also need to discuss frequency. And frequency is the number of vibrations per second. And usually that's in units of hertz, not the car rental company. And those are usually designated as Hz. Okay, and there's a point. When you talk about the various frequencies, you have everything from 63 all the way up to, I think, about 16,000 frequency. Anything below 1,000 is indicative of a low frequency. These type of waves are very long. They're very difficult to control. If you've got equipment that has a low frequency, you have to almost totally enclose it because it will find ways around things, through things, very difficult to control. And you have those frequencies that are high frequency, which are greater than 1,000 hertz. And these typically are shorter wave patterns. They're easier to control, so you can control them with sound barriers, other materials in order to reduce that noise level. When we talk about noise, it's really undesirable sound. And some of the more obnoxious type of noise is the high frequency noise versus the low frequency noise. Although when those teenagers pull up with that car and they've got the bass vibrating and you can feel the shock waves coming through your car, I sometimes wonder whether the low is more obnoxious than the high. And you also have pure tones, which are more obnoxious. So you got that constant at the same frequency, and it gets a little old after a while. It's kind of like the Chinese water torture. Another term that we need to bring out with respect to this type of monitoring are what are sound levels measured in. And typically, sound levels are measured in decibels. And it's a logarithmic function. It's not the straight additive effect at all. It's a logarithmic. So an increase of 10 dB seems like the sound has doubled. Just to kind of give you a flavor, here are some of the various sound levels that cause different reactions, or at least you'll hear it differently with respect to the individual themselves. Once you get up above a construction site, you're around 100 decibels. Things are starting to get pretty noisy. With respect to the noise monitoring instruments, they employ a frequency of weighing filters. And these are for the use of perception of sound or loudness. There are three types of weighing: A, B, and C. A is the one that you'll typically see in use 99.9% of the time, because it approximates the frequency with which we hear. So it mimics what we're hearing, or at least that's the theory behind it. The B and the C, the B is used for higher sound levels, and C is for blast wave type of functions. Again, these are seldom used. Usually A is what you're going to be using with respect to measurements. And there's also something referred to as the exchange rate. And what the exchange rate is there's allowed exposure time is cut in half when the exposure increases by 5 dB. So for every 5 dB, there is a halving of the time allowed. They also refer to this as doubling, and what you're doing there is for every exposure that you decrease, you basically double the amount of time that you're allowed. It's kind of a half one, 3/4 of the other. But the idea is the higher the decibel level, the greater the chance for, or the less time that you can spend before you're overexposed. These are the typical of the types of monitoring instruments. You have a sound level meter, and those are usually used for surveys. And then you have dosimeters. And these are some newer versions, still used to the type where you wore it and then you had a cord running up with a little microphone. These you just mount to the shoulder and you take it back and you download it. They're really slick. And the thing of it is these are somewhat non-directional, and you can get differences between what you get on a sound level meter as far as the reading on a noise dosimeter, because as they're mounted up on the shoulder, depending on where that noise is coming from, your head can act as a sound absorber and absorb some of that sound, so you may see a difference between one reading versus a sound level meter versus the noise dosimeter. Kind of like what my mom used to say, your head's a little dense. Well, probably comes in handy in this particular case with respect to absorbing some of that sound. And here's just a picture of a noise dosimeter in action. My associate helped out on these, as well as the microphone up here. We're getting ready to do a study of a leaf blower. And as far as exposure limits go with respect to noise, OSHA has a standard of 90 dBA as an 8-hour time-weighted average, and that's based on a 5 dB exchange rate, as we mentioned before. So every time you go up 5 dB, it's halved. And if you've got individuals that have a time-weighted average exposure of 85 or over, they're supposed to be entered into a hearing conservation program. The ACGIH, which again is the American Conference of Governmental Industrial Hygienists, they have an 8-hour time-weighted average of 85 with a 3 dB exchange rate. So what that means is that their TWA is 85, and then every 3 decibels down from that, you have your, you get exposure or less time for exposure. Okay, so as it increases, the exposure time goes down. That covers a big topic, a huge topic. If anybody wants the slides, there's my number. Feel free. I want to give special thanks to one of my colleagues, Andrew, who helped in this effort. Before we go, if you could plug me in one more time. If anybody has any questions. Yes?